Okay, hello everyone. So welcome to this course on life cycle assessment. So in this course we'll be covering basics of sustainability, sustainable engineering concepts, and also we'll go over water demand, energy demand, the water flow, energy requirement for different processes, different environment, different industrial processes. And initially what I will do is I'll give you a background, some introduction, and then we'll go individually in topics in more great detail. So a little bit background about myself. I am the instructor for this course. This is a 20-hour course, and I have BTech in civil engineering from IIT Kharagpur. Then I worked in industry for a little while. Then I did my PhD and have worked as a research scientist. Then have been teaching and doing research in the area of waste management, sustainability, sustainable engineering, life cycle analysis for almost 7-8 years now. So, and this course, as I said, it's a 20-hour course. We'll have 8 weeks. At the end of each week, there will be weekly assignments. We'll have videos of 30 minutes for every week. We'll have 5 videos and an assignment. So 2 hours of lecture videos per week, and there will be a final exam at the end. So these are some of the materials and textbooks which you can you can find for this course. The first one goes over the sustainable engineering basics. As you can see, it's a concepts, design, and case studies on sustainable engineering by David Allen and David Stronard. It's a Apprentice Hall. The ISBN number is provided to you for if you want to purchase it. You can get it from Amazon, Flipkart, or any of those websites, and also many of the bookstores will have it. And the second and third item is you can download. They are freely available from the web, so it's can be downloaded from there, and we will be referring to these material from time to time in different lecture slides as we progress into this course. So coming to the introduction, why, first of all, in any course, first thing you need to understand is what is the importance of this course, why we need to how this course was evolved, what is the need of the course, why people need to understand about these concepts. So as the world is growing, including our country India, we are making progress. We are using more and more natural resources, and we are making a lot of industrial activities. Industrial plants are coming up. So when all these things happens, there will be depletion of natural resources. We need to, at some particular point of time, you need to start thinking about, okay, we cannot get newer natural resources anymore, so we have to start recycling more and more. And so we'd say, and there will be some environmental implications too. Like whenever you do any industrial activities, you will produce certain emissions, whether it's an air emissions, water emissions, soil pollutions. Based on your previous environmental engineering courses or environmental science courses, you know that these are very important, like water, air, soil. These are very important part of our how we interact with Mother Nature. So keeping them clean, keeping them pure is very important. And why this industrial activity is needed? What is there is a lot of demand. Our population is going up. We are right now more than 7 billion people. India itself is 1.2, 1.3 billion. China again slightly more than India right now. So populations are growing up. As the population is growing up, at the same time, affluence is also going up. The affordability of the material, affordability of certain products. So if you remember 15-20 years ago, having just one TV in the home was considered like a kind of luxury, I would say, maybe in mid 80s and early 90s. But now if you go to a middle class house, there will be multiple TVs. Every bedroom may have a separate TV. So because it's affordable now, based on the income of the people, these cost of these electronics and cost of these many products is not that high. So people can buy those products. So when people are able to buy those products, what that means? That means there is more and more demand for that product. So with the more demand for the product, more product needs to be made. And when more products needs to be made, that means more raw material needs to be extracted and they will be manufactured. So there is a demand on raw materials, and there will be demand on there will be demand on water, because I will show you later on in one of the slides that water is one of the most essential item for any industrial activity. You need good water for any good plant, so any production going on. So there will be demand of all those. There will be water demand, there is a land demand for setting up all these factories, there will be a demand also for mining activities, there will be a demand for energy, because you need energy to do anything, and there will be emissions coming out, because whatever when you produce energy, there are emissions. When you make any plant, when you make a plant or make products after the plant is commissioned, that also have a lot of emissions coming out. So those needs to be tackled. So there will be air emissions, water emissions, impact on land, and of course demand for more and more raw materials. So what is happening is, since the population is going up and we are using lots and lots of raw material, and we are creating a lot of emissions going into the environment, there is a concern that what will happen in the future, whether we will have these resources available for our future generation, whether our grandchildren will be able to enjoy the same level, same lifestyle, or they should enjoy even a better lifestyle than us. And for all that, they also need natural resources. So how to make the whole concept of this sustainability or the sustainable engineering is how to use the present material, the present resources in a way so that our future generation can make use of that as well. So that's the whole awareness of that, which started around mid 80s with the United Nations some initiative. So the whole awareness of that and then implementation of that in our day-to-day life. When I say day-to-day life, means industrial practices and other practices. So how to take care of today's demand, at the same time make sure that the future demand is also met, and that's raised to the concept of what is known as the sustainability. So sustainability, this is a definition from the UN document, which was the Brundtland Commission, which first looked into this concept. It meets the meaning of the sustainability. The way it is defined is development that meets the need of the present without compromising the ability of future generations to meet their own needs. So as I said earlier, we can meet today's need, but at the same time, say our grandchildren, our children, or great grandchildren should be able to meet their needs as well, so that resources should be available. So if you think about the items that are present on the periodic table, we cannot really destroy that material, we cannot create those materials. The amount of these materials are already given to us by Mother Nature. So there is a certain quantities of that. Some are more, some are less. The ones which are more, we call them abundance. So but that how we define is abundance of one element versus another element. Iron is one of the most abundant element, but most of the others are not. Many of the items that gets used in electronics, for example, you hear the term rare earth metals. Rare earth, by the name itself, if you just go by the English of it, rare means something which is not easily available. So it's there, they are not abundant in Mother Nature. So anything, as I said, anything on the periodic table has certain like a quantity present in the Mother Nature. So as we are using these quantities, of course it will rain out at some point of time. So those who are most abundant will rain out over maybe 100 years or 1000 years. Those who are less abundant or the rare will run out much quicker. So how we can use this in a way so that our future generation can make use of these material as well. So after we use it, we should not make it in an unusable form, send it to a landfill or send it to a certain place where you cannot use it anymore. So this whole concept came is how to meet the need of the present without compromising the future. And this whole, then the concept of sustainable engineering, green engineering, pollution prevention, all these are interchangeable terms to some extent. They overlap with each other and they come under big picture umbrella of industrial ecology and all that. And so when you go for any of these sustainability activities, as an engineer or as a practitioner, you need to make sure that you measure the sustainability parameters. So how to measure the sustainability parameters, there comes this concept of life cycle assessment, which we will explain in this course as well. So sustainability, as I said, it's a very powerful concept, as I was trying to explain you. It's a very powerful, but it gets abstract. What is sustainable, what is not sustainable? Many times when you talk to people regarding sustainable, people get confused between sustainability versus durability. Those are two different things. Durability does not mean sustainability. So it's a powerful concept, but as I explained earlier, but it's an abstract. Since it's new relatively, So it gets very difficult to understand that. And as an engineer, or we as an engineering, we want to incorporate the sustainability practices in our product, process, or systems. So when you try to incorporate something, you need to measure that. You need to measure, otherwise how will you incorporate? Say if you want to compare process A versus process B, so you need to have some sort of quantitative measurement so that you can compare this to say that okay, process A is better than process B, or they are equal, or what, or the vice versa. So for those incorporation, we need to have some sort of mathematical formulation, and LCA, life cycle assessment, helps in that mathematical formation. And when we talk about sustainability, so far what I have been talking is mostly from the environmental standpoint. But sustainability, if you have looked at this particular concept, we say it has 3 pillars. There are 3 pillars of sustainability. One is environmental, and LCA does only the environmental part. So not the way that we do LCA, there is a social LCA as well, and for there is an LCCA, life cycle costing assessment, which takes care of the economic part. So there is an integration of the environmental, economic, as well as the social factors in the design. That's the overall sustainability. LCA that we will be learning in this course will be focused mostly on the environmental part. We may touch a little bit on economic and social, but we will be focusing, our main goal will be looking at the environmental side. Now we are trying to convert the concepts, this different concept, into quantitative design tool, as I said, and then you look at some matrices so that you can apply an engineering design, so that you can compare 2 different engineering design. So that's is like a basic concept of where the sustainable engineering comes. And there is a magnitude of sustainability challenge, as I said very earlier today, that our population is growing up, people's affluence is going up too, and technology is also keeps on improving. So there is an equation which is presented. It's called IPAT equation. This IPAT equation is essentially where I is what is the impact. That's the equation relates to the impact, and with respect to the population, multiplied by the affluence and multiplied by the technology. So when we say multiplied by affluence and multiplied by technology, we need to put some numbers to that, and we'll get to it in a minute. So essentially the concept was developed to see, okay, what is the magnitude of the pressure on resources and ecosystem? Our population is going up and our affluence is also going up, and when we talk about technology, we need to get more and more efficient technology. So if we can have much better efficient technology which can take care of the population increase. So if you have a 10% increase in population, and at the same time you make your process efficient by 10 to 15%, the impact will be more or less the same, because now when we say increase in population, we are talking about increase in demand. So it's A as like affluence part is, as people are getting more and more affluent, there will be more demand as well. So both, whatever is the increase in P and A, if we can take care of that to increase by making our process more efficient, that nullifies the pressure that is coming from P and A. If it's not, then we will have more and more pressure. When we say pressure, essentially it's pressure on natural resources and also the emissions coming out into the environment. So this concept was came in by Ehrlich and Holdren in 1971. They came up with this equation, and to look at like in example, so world population right now is increasing at 1 to 2%, and it is said that around we will go up to around 10 billion, and then we will peak, and hopefully after that there will be no further increase, the population will stabilize. But these are all based on some predictions. Then if you look at the affluence is related to the GDP growth, and which is max around 8%, average is around 2 to 4%, and that's the global average. Countries like developing countries like India, China, they are progressing as much higher level than most of the developed countries right now, because they are already developed, so they have a big base. So our base is small, so our GDP growth comes out to be much bigger. So, but if this trend continues for some time, if this trend continues for several decades, so we have an increase in population, we have an increase in affluence. So this will lead to world economic output needs to increase. That will increase by around 50% in 10 years, and maybe around 300% in 25 years. So it's so let's say more than a factor of 10 in 50 years. So if you put the IPAT equation into this picture, if the technology doesn't change, say if the technology stays the same, what we are looking at is the material use and the environmental impact will grow 10 times in 50 years. And we have seen that over the last, after the World War, we have which was in mid 40s. It's 70 years before that we had the Second World War, after which the Industrial Revolution is started. So there are many areas, especially in the developing countries, the technology has not really gone in a much efficient way. We are still using outdated technology. We are still using things which is in a very I would say crude way. And so if the technology remains static, so our energy use, material use, and environmental impact will grow 10 times. So we are in a and we have more demand on the Mother Earth. So we need to reduce the impact. So to reduce the impact by a factor of 10 to support 10 billion people, so it's because all they want to have a better living standard. So we have to reduce the impact by a factor of 10 to support the growing population. So that's kind of a big picture of how like affluence and population increase has an impact on natural resources requirement, also an impact on how the environmental emissions will come out. Then if you look at for any of these industrial activities, you require energy. Without energy, there cannot be any industrial activity. So you need some form of energy. And if you can see over last some 25 some years, 30 some years, still there is the total energy demand, which is the top graph. You see the top line, the dotted with those circles. You see the energy is going up. We need more and more energy that is required. Then if the different contribution that is coming out in terms of from different sources, coal is still produces. We still have a lot of coal energy, which is the second line. The triangle is your coal, and then on top of that is our natural gas. Natural gas is more than the coal. Then we have some supplies coming up from nuclear and renewable, which is not that high, which is both of them at the bottom. So that's coming out. So in terms of different supplies that is coming out, coal is still, in a country like India, we have more coal power. Coal dominates the energy mix, and we have been talking about that we will run out of these. When the coal, natural gas, or the oil, these are all called fossil fuel. So if you follow the newspaper, if you follow the different websites, you hear from time to time that we will have more and more. We need to go for more and more renewable energy. We need to go for more and more, say, solar power. Solar even doesn't, renewable here potentially includes solar as well. And so we need to have more and more solar power. We need to have more and more wind, geothermal. So those are considered as a renewable energy. So we can, but other than the fossil fuel, where you have coal, natural gas, mainly oil, these liquids, they will run out. They at some point of time go for this alternative energy. So, but the nutshell here is there is a lot of energy requirement, and energy is needed for different activities, and and you cannot have any industrial production without energy. So this is one example of how in the US different energy sources. You see the petroleum, which is number one in terms of supply, then natural gas, coal, renewables, and nuclear. On the right hand side, you see the demand sector. Transportation sector has highest demand, then industrial, residential, electrical power has the highest demand. And you see that electrical power, a lot of electrical power is coming from nuclear, some from renewable, a lot of it coming from the coal, some natural gas. So there are different sources which takes care of the supply. But many of these, if you look at the renewable, that's only 7.3%. So it's a lot of is going through the fossil fuel. So when you look at primary energy production from the different countries, here again China is that's at the bottom. You can see the purple is our coal, and that's coal dominates in many of the developing countries, and also like some of the rich countries as well. Australia, and they use a lot of coal. Germany has been using quite a bit of coal as well, but they are moving. Many of these Western European countries or the developing countries, they are now trying to move away from coal and go for other form of energy, like a non-fossil fuel energy. Again, if you look at in terms of production and consumption, India we are consuming more than what we produce, so that's why we import. And same holds true for China, US as well. US imports a lot of energy. Some of the countries which can produce more energy than they consume includes Russia, Canada, Australia, Norway, and those are the countries which are energy supplier. They can export. Again, these are 2008 data which came out in a 2012 report. So you need to, the present figure may have changed a little bit, but for the big picture it will be almost the same. So energy is important, but at the same time, a country like India, there is a lot of energy loss in electrical power generation, and also a lot of, because of our efficiency, we lose a lot of energy in the waste heat released at hot water and hot gases. When fossil fuel gets burned to heat, converted to mechanical work, and then these processes are not that efficient. So there is a loss in electrical power generation. At the same time, there is a loss in electrical power transmission, and there is a lot of theft as well. So if you look at different stuff that we use, most of the time you see steam turbine or coal-based thermal power plant. They will produce steam, and the steam turbine is used for energy. It's only 45% is energy efficient. So again, 55% of the energy is lost when we use a steam turbine. Fuel cell is 60%, so fuel cell is better, but microbial fuel cell or any fuel cell technology, they are much expensive, so that's why you don't see that much being used. Fluorescent light that we use in our home is only 22%. Incandescent light, the old bulbs that we used to use, is only 5%. Internal combustion engine 10%, human body around 20 to 25%. So if you look at, as an engineer, there is a lot of scope for us to improve these efficiencies. So if you improve these efficiencies, of course it will help in our sustainability goals. And these are some of the other device efficiency. You look at the dry cell battery, 90%, home gas furnace 85%, storage batteries, a home gas furnace is better than oil furnace. Then you have a small electrical motor, and you looked at the incandescent lamp. So as you can see, for the different devices, the intensity efficiency is very, it kind of goes down. We have efficiency goes down to a lower efficiency as we make progress. And then it gets compounded. It gets compounded because we have full input of 100 at the beginning. Around 70% get lost in the power plant itself, with all the processes happening in the power plant. Then there is a transmission and distribution loss. Then you have a motor loss and drivetrain loss, pump losses, throttle loss, pipe loss. So ultimately, out of 100 unit, only nearly 10 unit gets used up. So think about lot of opportunities as an engineer, not only electrical engineer, but all sorts of engineering discipline has to kind of put their brain here to reduce all these losses, and that will lead to a better our goal towards the sustainability. So that's and we have to, as an engineer, we have to continuously improve energy required per unit of economic output. And when we improve our energy, that reduces cost and it conserves natural resources. And when it reduces conserved natural resources, it also reduces in the environmental impact. So there are environmental impact is associated with energy consumption. As I showed you earlier, fossil fuel is still used a lot, and that release carbon dioxide, which is a global warming gas. Combustion also releases oxides of nitrogen and some fuels, sulfur, into the air. So photochemical reaction, they convert them into ground level ozone and acid rain. So that's hydropower can cause land inundation. It's habitat destruction and alternation in groundwater and surface water flow. So there are environmental impacts associated with these. Nuclear power, the problem is how to manage, of course, in the mining, uranium mining, as well as how to take care of the nuclear waste. Recently, we have a tsunami in Japan, and if you have followed the news, we had a big issues of nuclear waste management. Renewable fuel, in Indian context also, we are worried about nuclear fuel management. That's one of the area where it needs a lot of attention. Renewable fuel, wood has been used as renewable fuel, but it leads to a lot of widespread deforestation because we are using wood in a much faster rate than what forests can produce it for us. Solar panels, they are good in terms of energy, but if you look at from the big picture on the life cycle, there is a energy intensive use is there in the heavy metal and creation of the metal waste. So to make the solar panel, a lot of energy, it's a lot of energy is needed there. So that's in a nutshell we have been talking about in so in terms of this particular course. So this is a life cycle assessment course. This it's where we will be looking at some of this, what is the need. So what I was trying to explain over the last 25 some minutes is to see why this course is needed. So we need energy for everything. For our house also we need energy from early morning to late evening, even during the night. During the summer months you need to have your AC going on, and also your fans going on. So energy requirement is there, and we have the resources requirement. So energy resource is needed for any of these industrial productivity. There is a growing population, there is growing affluence, the affordability of different of the section of society is going up. Even if the Indian context, if you drive around, go to the villages and other places also, when you drive on the road, you see these days, you will see more motorbike than the manual bicycle. That again kind of shows us that people's affordability have gone up. People have kind of graduated from bicycle to motorcycle, and the people who used to drive motorcycle earlier has graduated to small cars. So that's and for all of these there is a resource demand, there is a demand for energy. When the industrial production needs lots of water, there will be a lot of waste produced. Waste will come out in different form. Either it will produce like air pollution issues, water pollution issues, and like a soil. If you are using if you look at the cotton industry and other industry, if you are using a lot of fertilizers, where if you are getting a lot of stuff from the agricultural field into your plant, so uses of multiple fertilizers, different types of insecticides, fungicides is also having impact on the land quality, the soil quality. So all these factors needs to be incorporated when we are trying to look at a big picture impact. What happens is so far, if you look at any of the industrial process, we have been taking a silos approach. When I say silos approach, we look only at one particular aspect or one particular unit. We don't look at things in a big systems approach, in the entirety. So this life cycle assessment is basically to forces us to look at an entirety. So we need to look at from the cradle to grave, and sometimes even from cradle to cradle, which we'll talk about later in this course. So where we say, even if you want to make a want to find out what is the environmental footprint of this particular product, it's just a simple sketch pen. So it makes of plastics, different material goes in there, could be different metals, it uses ink. So we have to look at all the raw material that got to manufacture this, what was the environmental impact associated with that, during use, how we are going to use it, when we throw it away, whether it is going to a landfill or to a waste to energy plant, and how this will be impacting environment there. So all these factors needs to get to be incorporated and put together as one exercise, and that exercise is your life cycle assessment exercise. So as you will make progress in this course, you will see several examples, and which will get this concept more clearer and clearer. As the beginning, we are trying to go over some of these basics of why this course is important. As I said in the very beginning of the class today, you need for any course, first thing you need to really you have to really think about that why I am studying this course. Once this why factor is taken care of, when you understand the why factor, when that will help you develop interest in this particular course. And once you are interested, you will learn the other part. You will be more interested to make progress. So with that, we will try to wrap up this particular like a lecture, the first video lecture for the week 1, and I'll see you again for the second part of the half an hour video lecture. Thank you.